Audio Jungle.
Let's start with introduction of chapter Complex Integration. Complex number. For understanding complex integration, first you need to know what are complex numbers. If you know complex numbers properly, then you can understand the chapter easily. Complex number is divided into two parts, real and imaginary. In general, we write the complex number as z equals x plus y. Here, x is real, y is imaginary, and value of I is root minus 1. Geometric representation of complex number. Complex number is represented on Argand plane as a point. In the diagram, we can see the point represented in the plane as x, y, where x, which is a real number, is termed as abscissa, and y, which is an imaginary number, is termed as an ordinate. The real and imaginary part of complex number are coordinates x, y. Earlier, functions were of real numbers, but in complex integration, the functions are both real and imaginary. Thus, function of z will have z as a complex number. Here, the function of z equals z square. So, to find out the real and imaginary part of the equation, we put z equals x plus y. Thus, we get x plus iy the whole square. Then expanding using a plus b the whole square, we have x squared plus 2ixy plus iy square. As value of I square is minus 1, so we get x squared plus 2ixy minus y square. Here, x squared minus y square is real, and 2ixy is imaginary. We write it in the form f of z equals u plus iv, where u and v are both functions of x and y. Analytic function. Function of z is said to be analytic in a particular region if it is differentiable in that region. Conditions for analytic functions are: f of z should be single-valued. For example, you can see that 4 square is plus 16, but root 4 is plus or minus 2. Here, plus 4 square is of single value, and root 4 is of multiple value. F of z should have unique derivatives with respect to z at each point of its domain. Last condition is that it should satisfy Cauchy-Riemann, that is CR equations. For Cartesian form it is dou u upon dou x equals dou v upon dou y, and dou v upon dou x equals minus dou u upon dou y. And for polar form it is dou u upon dou r equals 1 upon r into dou v upon dou theta, and dou v upon dou r equals minus 1 upon r into dou u upon dou theta. CR equations alone are necessary, but not sufficient to check whether function is analytic or not. Let's start with our main topic, complex integration. You've learned integration with real variables before, where area under the curve is considered, and it is cut into smallest infinite pieces at equal distance xi. In the given diagram, you can see the area under the curve, y equals function of x is cut into number of pieces at a distance of delta xi. The curve has limits from a to b, so we get the equation as integral of a to b f of x dx equals limit n tends to infinity summation f of xi into delta xi. Taking n tends to infinity, that is delta xi equals 0. This is the real integral, where only real variables were considered while solving the equations. Complex integration. In complex integration, curve is considered, and is cut into infinite pieces. Here, you see the complex integral, where limits and function are complex variable. In the given diagram, you can see the curve with equation y equals f of x with endpoints a to b. This curve is cut into infinite pieces. Let the ith piece be z I minus 1, and other be zi, and xi be the point between the pieces, and on the curve. The equation we get is the product of functions xi and delta zi. Here, delta zi is difference between zi minus z I minus 1. The equation will be limited as n tends to infinity, and taking the sum of all the pieces with product of the functional value and the piece distance. This integral is called as integral over C. Evaluation of line integral. In integral over C, which is the complex integral, we know that function of z is u plus iv, and value of z is x plus iy. By differentiating z, we get dz equals dx plus idy. Substituting these values in complex integral, we get integral over C, u plus iv into dx plus idy. After multiplying the terms, we get real and imaginary values. In the previous diagram, equation of the curve was y equals f of x. After differentiating y, we get f dash x dx. To evaluate further, we have to convert the full equation in either x or y. So, converting y as a function of x, we substitute the above values. As we will have the values as function of x, we write the equation as integral x1 to x2, g of x dx, where g of x is the function of x. And to convert x as a function of y, we will have the equation as integral y1 to y2, h of y dy, where h of y is the function of y. Points to remember while solving the problems. The equation will have two variables. Thus, to solve the equation, you should convert the equation in single variable, and then evaluate. After converting, you will have the equation as function of x, or function of y. Steps to solve the problems. Step 1 is, look for given equation. If not given, then you should calculate the equation based on the question, using the 2-point formula, y minus y1 upon x minus x1 equals y2 minus y1 upon x2 minus x1. Step 2 is to take the derivative of the equation. Step 3 is to convert the f of z and dz in either x or y, where the conversion is dependent on the given equation. Step 4 is to substitute the converted equation in the problem. Step 5 is to integrate the converted problem considering the limits of the same variable. That is, if we convert the equation as function of x, we should consider the x limits, which are abscissa, and if we convert it as function of y, then we consider y limits, which are ordinates. Contour integral. When C is a closed curve, then we call it as a contour integral. It is denoted as contour integral C, f of z dz. Physical significance of complex integration. In the diagram, you can see a particle with applied force F covers a distance from A to B. But we know that work done equals force into displacement. So integral over C, f of z dz, will give the work done by the particle. Here, f of z is the applied force, and dz is the displacement.